So we have an inclined plane in this diagram. We can see that the incline has an angle, excuse me, there we go, try that again, here. Some angle that the plane has been lifted to, and this is a free body diagram. These are the forces that are acting on an object that's at rest on an inclined plane. So obviously we have the weight of the object acting down. Because the object's stationary, it's not sliding up or down the plane. We have friction that's holding it in place, and we have a normal force that acts perpendicular to the plane. So it's really important to remember now that our normal force and our weight, or our force of gravity, are no longer equal and opposite to each other, because that normal force must act perpendicular to the plane, and the weight always acts straight down to the middle of the earth. And so these are the forces that are acting. There might be another force involved where you have some kind of applied force acting up or down the plane, but generally this is what you're looking at when you have an inclined plane. So you might be going, well, I don't know what I'm going to do with this, and I can understand that, and because now we've got things at funny angles. So what we do is we tilt our Cartesian plane, and we treat the plane as our x component and the perpendicular to the plane as the y axes. So we have our x and our y, and they're acting along the plane. And our weight is going to be, as I say, is acting straight down and forms a right angle here. So what that tells us is the angle here is 90 minus theta, which means that the angle between the weight and the y component, or the y axis, is equal to theta, because this also is a right angle. So as a result, we know that we have an angle of theta acting between between the y-axis and the weight. And that's actually how we would calculate the magnitude of our normal force. So think of the normal force is equal and opposite to the component of the weight that's acting perpendicular to the plane. So we call this the force perpendicular. Some people call it the weight perpendicular. But it's the component of the weight, or the component of the force of gravity, that's acting perpendicular to the plane. So, and then we have a component of that weight that's pulling down the plane, right down the plane like that. And so it's acting on the object, pulling it down the plane. And if the object is stationary, we know that the friction and that force pulling it down the plane have to be, again, equal and opposite, because they are the object is stationary, and so they're balancing each other out. And we call this the force parallel, or the weight parallel. And it's the component of the weight that is acting parallel to the plane. So they don't belong in a free body diagram. They come after you've got your free body diagram that analyzes all the forces that are there, and then we break the weight into its components. And we can calculate that force parallel right here. Okay, so we can see its magnitude comes from this leg of our right triangle, and this is our right triangle here. Okay, so recognizing that our angle is here, our force perpendicular is adjacent, and so we take our weight, or the force of gravity, and we multiply it by the cosine of our angle. And we always calculate the perpendicular force, or the perpendicular component of the force of gravity, by taking the weight times the cosine of the angle of incline. Our parallel component is opposite that force of or opposite that angle, and so we use the sine, and we calculate that by using the force of gravity, or the weight, times the sine of the angle. And often it's written here because we think of it as acting up here. So we can write it here, our weight times the sine of the angle. And it's right there. So often in the initial questions you'll have frictionless surfaces, but if you have an object that's stationary, we know that the normal force is equal and opposite to the perpendicular force. So we're just going to make these magnitudes by putting the absolute values in there, and we know that our force of friction is equal to the force parallel, and again opposite in direction.